liquid petroleum gas LPG, okay, is used as a fuel to generate steam in the boiler. The composition of LPG is 30% mole of propane and 70% mole of butane. The air is fed uh, for combustion is completed and the system is adiabatic. Calculate the standard heat combustion of 1 kilomole LPG and the theoretical flame temperature if air is fed at 100 degrees Celsius and the fuel is fed to the furnace at 25 degrees Celsius. So this table is given data of the combustion, standard combustion at 25 degrees Celsius for different kind of fuel. Okay, so the step to solve this problem is not different than the one before. Okay, as you notice that now instead of having one fuel, you have two fuels, and then the inlet temperature is not the same, it's not at the standard for the air. Instead, it is provided at a temperature of 100 degrees Celsius. Okay, how to do this one? So first of all, we check from the thermodynamic data. We know from the problem that for 1 kilomole of LPG, there is 0.3 kilomole of propane and there is 0.7 kilomole of butane. And then based on the table of the heat combustion, we know that for the propane, it has this amount of heat of combustion, and for butane you have this amount of heat combustion. Okay, so we can calculate the heat combustion. Simple. The heat combustion of LPG equal to the total of the two, 0.3 kilomole of methane times the standard heat combustion of methane plus standard heat combustion of butane multiplied by the amount of the butane. So we have this. This is basically delta H2. Next, we look into the reaction. Okay, we look into the reaction. We have two reactions. As you can see here, first, this is the full combustion of propane, and this is the complete combustion of butane. So I keep saying about complete combustion because there is a possibility that methane or butane here undergoes a partial combustion. So when it undergoes partial combustion, you have one more reaction that produces carbon monoxide instead of carbon dioxide. So if there is a possibility of having a partial combustion here, so basically we have two more reaction. So here is the partial combustion of propane, and here you will also, number 4, you will have also partial combustion of the butane. So to continue, we assign all of the number based on the basis we use. So we have a 0.3 kilomole of propane here react stoichiometrically with oxygen from the air. You produce this, and then another one you have 0.7 kilomole of butane here react with this amount of oxygen stoichiometrically to produce these products. We sum up the two, and basically this is our overall reaction. Okay, this one is overall reaction, but remember that this overall reaction is the one achieved through a stoichiometric feed of the air. In our problem, the air is produced 20% in excess. What does it mean? If you look here, so the theoretical, so the stoichiometric requirement of oxygen is 6.05 kilomole. Okay, since we provide it in excess, so here we add 20% more air. Okay, we add 20% more air. Also, since we add 20% more air, we also so when we add air, we also add nitrogen, which is for every mole of oxygen we need to provide 3.6 I forget 3.76 mole of oxygen, and this is the total reaction become. You look here that uh, for the stoichiometric reaction we have no oxygen in the product, but now we have an excess oxygen. So this is basically oxygen that we provide in excess to the system. And we also have the E naught of nitrogen. Sorry, here it's a typo, it's supposed to be nitrogen. Okay, um, to make it simple, it is always advised to make a block flow diagram like this one. So basically this is a combustion chamber. We have a fuel with this composition, and we have an air with this composition. Yeah, we have a 7.26 kilomole of oxygen and 27.3 kilomole of um, nitrogen. You burn this one, and then you have the combustion product. Yeah, CO2, hydrogen, the excess of oxygen and nitrogen there. Then we apply the Hess law in the system. Basically, what we know as the system is adiabatic, so delta heat combustion equal to 0. So the next one is we need to find out the delta H1, delta H combustion standard that we calculated before, and we have a delta H3 when you try to increase the temperature from the standard condition to the theoretical flame temperature. So delta H1 is easy. So we have the air at temperature of sorry to the air come at sorry the car and sorry the air enter at temperature of 100 degrees Celsius. So T in here is 100, okay, plus this one to the standard condition 35 degrees Celsius. So this is mole times the Cp average. This is the mole of nitrogen times Cp average plus the fuel. So since the fuels coming at temperature of 25 degrees Celsius, so this is the standard temperature, then basically the second term in this equation is equal to 0. So we then calculate the delta H1 equal to minus 75,916 kilojoule. Okay, delta H2 is basically the standard combustion of LPG we have calculated before to have this number. And then lastly is delta H3 when we increase the temperature from the standard temperature to the TFT, theoretical flame temperature. So the same process as in the example one. So we just guess first. So our guessing now is 1500. So you bring in delta H3 equal to yeah, this equation, the total mole of CO2 multiplied by the average Cp of CO2, and then 4.7 here is the mole of water. Okay, the total mole of water multiplied by the average heat capacity of water. Next is oxygen. Okay, oxygen, total mole of oxygen multiply by the average heat capacity of oxygen, and lastly the total mole of nitrogen multiplied by the average heat capacity of nitrogen, then multiply by delta T, which is the theoretical flame temperature minus 25. Then all of this long equation is simplified into this one. Then we perform the balance, bring in all of the equation we find before. We find out that the TFT is equal to 2108 degrees Celsius. This answer is too far away from the value we guess. It's more than 5%, so it's not acceptable. So we need to do another guesses. Now we make it closer to the solution here. In our previous guessing, we guessed too far, too small. So now we guess it a little bit higher. So our second guess in iteration is we guess it at theoretical flame temperature of 2100 degrees Celsius. So then you calculate delta H3 the same way as we calculate before here. Okay, the only difference is you have to look into the correct value of delta, uh, the correct value of average heat capacity. Okay, it has to fall within the range of the guessing here. So by by calculating all of the term in this equation, you can simplify into this form, and then apply the Hess equation to solve the balance. We find out that the temperature equal to 2324 Kelvin, or about 2051 degrees Celsius. This solution is acceptable because it's deviate less than 5% from the guess value.